In April 2019, a team of over 200 scientists released the first photograph of a black hole. It was not an illustration. It was not an artist's impression. It was a real image, captured by 8 radio telescopes spread across 4 continents, linked together to form a virtual telescope the size of the Earth, pointing at a galaxy 55 million light-years away. The image showed a bright ring of superheated gas, glowing orange and gold against the black of space, wrapped around a circular shadow at the center. The shadow was the black hole itself, the region where gravity is so strong that not even light escapes. A hole in the fabric of observable reality, visible only because the light it swallowed outlined its own absence. The press conference where it was released was broadcast live around the world. The lead scientist, Katie Booman, had written the algorithm that made the image reconstruction possible. She had started the project as a graduate student. The photograph was the culmination of years of work, involving petabytes of data, atomic clocks, and the coordinated observation schedules of telescopes in Antarctica, Hawaii, Chile, Spain, Mexico, and Arizona. It required more computing power than most universities could provide. And when it was finished, when the first image resolved from the noise, what they had was a blurry orange ring 40 microarc seconds across. A circle you could cover with a penny held up against the sky from across an ocean, showing the boundary between the observable universe and something that is, in the most literal physical sense, beyond it. We have a photograph of a black hole. We have the shadow of an object from which light does not return. And yet the photograph is, paradoxically, the least mysterious thing about black holes. The image shows where they are. It does not show what they are, what happens inside them, what they do to time and space and information and the fundamental laws of physics. And it does not resolve the increasingly urgent theoretical crisis that black holes have generated at the intersection of the 2 most successful theories in the history of physics. This video is about all of that. It is about the strange, deeply counterintuitive physics of black holes. Not just the popular summary version, but the full, vertiginous depth of what we actually know. It is about the event horizon and what crossing it means. It is about Hawking radiation and why it threatens to break physics. It is about the information paradox, a problem that Stephen Hawking spent the last 40 years of his life trying to solve, and died without solving, and about a recent development that may finally be pointing toward an answer. And it is about what black holes tell us about the deepest question in physics: how to reconcile the 2 theories that each describe their respective domains with perfect precision, but that, when combined, produce nonsense. The mystery of black holes is not primarily about gravity. It is about information. And when you understand why, the strange part is not that black holes are strange. It is that they are this strange. Chapter 1. What a black hole actually is. The physics without the metaphor. The phrase black hole is so embedded in popular culture that it has become almost meaningless. People use it as a metaphor for anything that consumes without returning. The actual physics of black holes is more interesting and more counterintuitive than the metaphor suggests, and understanding it requires starting from scratch with the geometry of space-time. General relativity, Einstein's 1915 theory of gravity, replaced the Newtonian picture of gravity as a force acting between masses with a geometric description. Mass and energy curve spacetime, and objects moving through curved spacetime follow paths that are not straight lines in the conventional sense, but are the straightest possible paths in a curved geometry. The Earth orbits the Sun not because the Sun pulls on it with a force, but because the Sun's mass creates a curvature in the space-time geometry that makes the Earth's natural straight line path in that curved geometry loop around the Sun. This is a genuinely different picture from Newton's, and it makes different predictions in regimes where gravity is very strong. The Schwarzschild solution, the solution to Einstein's field equations describing the space-time geometry around a spherically symmetric mass, was published by Karl Schwarzschild in 1916. Less than 2 months after Einstein published general relativity, while Schwarzschild was serving on the Russian front in World War I. He sent it to Einstein from the trenches. He died 4 months later of a disease contracted at the front. He never knew what he had found. The Schwarzschild solution describes the curvature of space-time outside a spherically symmetric, non-rotating mass. For most masses, planets, stars, people, the Schwarzschild solution is indistinguishable from Newtonian gravity at ordinary distances. The differences only become significant when you get very close to the mass, or when the mass is very compact. The solution contains something unusual, a specific radius, now called the Schwarzschild radius, at which the geometry of space-time does something extreme. The Schwarzschild radius is given by the formula R sub s equals 2gm/c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For the Earth, the Schwarzschild radius is approximately 9 millimeters, the Earth compressed to the size of a marble. For the Sun, it is approximately 3 kilometers. For the 6.5 billion solar mass black hole at the center of M87, the one photographed in 2019, it is approximately 20 billion kilometers, roughly 130 times the distance from the Earth to the Sun. What happens at the Schwarzschild radius? In the original mathematical description, the metric, the mathematical object that describes the geometry of spacetime, appears to become singular. Certain terms blow up to infinity. For decades after Schwarzschild's paper, physicists debated whether this was a real physical singularity or a mathematical artifact of the coordinate system being used. The answer, worked out in the 1950s and 1960s, is that the apparent singularity at the Schwarzschild radius is a coordinate artifact, an artifact of how you choose to label points in space-time, but that there is a genuine physical feature there nonetheless. That genuine physical feature is the event horizon. The event horizon is a surface in space-time, not a physical surface, not a wall, not something you could see or touch if you were falling through it, but a surface defined by a specific causal property. It is the boundary of the region from which no future directed path in space-time can ever reach the outside universe. On one side of the event horizon, all future paths, including the paths of light, can reach infinity. On the other side, all future paths lead to the central singularity. The event horizon is not a place where something dramatic happens locally. An observer falling through the event horizon of a sufficiently large black hole would feel nothing special at the moment of crossing. The tidal forces, the difference in gravitational pull between your head and your feet, are inversely proportional to the mass of the black hole. So for a supermassive black hole, like M87 star, the tidal forces at the event horizon are negligible. You would cross without noticing. What you would notice is that you can no longer send a signal to the outside. Not because anything blocks the signal, because the signal, traveling at the speed of light, follows future-directed paths in space-time. And all future-directed paths inside the event horizon lead inward, not outward. The event horizon is a one-way membrane in the causal structure of space-time. Things fall in, nothing comes out. This is the physical definition of a black hole, a region of space-time from which nothing, not matter, not radiation, not information, can escape, bounded by the event horizon, with a singularity somewhere inside where the curvature of space-time becomes infinite and the known laws of physics break down. The singularity is not in the center of the black hole in the spatial sense. Inside the event horizon, the coordinates of space-time are scrambled in a specific way. The radial coordinate pointing toward the singularity becomes a time coordinate pointing toward the future. The singularity is not a place you can avoid by steering around it. It is in your future. Chapter 2: How Black Holes Form, the Death of Stars. The theoretical prediction of black holes from Schwarzschild's mathematics was not immediately taken seriously. Einstein himself, in a 1939 paper, argued that black holes could not actually form in nature, that the process of gravitational collapse would somehow halt before reaching the Schwarzschild radius. He was wrong, but he was not obviously wrong. And it took several decades and the work of several major physicists to establish that black hole formation is a natural and inevitable consequence of the physics of stellar evolution. Stars are objects in which two forces are balanced: gravity, which pulls all the mass toward the center, and the outward pressure from nuclear fusion reactions in the core, which provides the thermal and radiation pressure pushing outward. A star is a gravitational machine that converts nuclear binding energy into the support structure that prevents gravitational collapse. It works as long as the fuel lasts. For stars, with masses up to roughly 8 times the mass of the Sun, the end of fuel means a specific sequence of events. The core, no longer supported by fusion pressure, contracts under gravity and heats up. The outer layers are expelled in a planetary nebula, the remaining core stabilized by electron degeneracy. Pressure, a quantum mechanical effect from the Pauli exclusion principle, which prevents 2 electrons from occupying the same quantum state, forms a white dwarf. White dwarfs are stable indefinitely as long as their mass remains below approximately 1.4 solar masses. Above that threshold, the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who derived it in 1930, electron degeneracy pressure is insufficient to prevent further collapse. For more massive stars, the end is more violent. When a massive star exhausts its nuclear fuel, the core collapses catastrophically in less than a second, releasing more energy than the Sun will emit over its entire 10 billion year lifetime. This is a core collapse supernova. The outer layers of the star are blown outward at a fraction of the speed of light in the explosion. The core, if it survives, is either a neutron star, stabilized by neutron degeneracy pressure, the the same Pauli exclusion principle applied to neutrons, which are much more compact than electrons. Or, if the core mass exceeds approximately 2 to 3 solar masses, nothing can stop the collapse, and the result is a black hole. A stellar mass black hole formed by this process has a mass of roughly 3 to several tens of solar masses. The Schwarzschild radius is correspondingly small, a few to a few tens of kilometers. The black hole is invisible except through its gravitational influence on surrounding matter or companion stars. There is a second category of black hole formation relevant to the very early universe: direct collapse. In environments with extremely high density and low rotational support, conditions that may have existed in some regions of the early universe, gas clouds can collapse directly to a black hole without going through the star formation and stellar evolution process. This pathway is proposed as one possible origin for the supermassive black holes, with masses of millions to tens of billions of solar masses found at the centers of virtually every large galaxy. The origin of supermassive black holes is one of the most active areas of black hole research because the standard stellar evolution pathway cannot produce them, even if every massive star in the universe's history had collapsed to a black hole, and all those black holes had merged. You would not have enough total mass to account for the observed supermassive black holes. The pathway from stellar mass to supermassive is not fully understood. The third category is primordial black holes, hypothetical black holes that might have formed in the very early universe from density fluctuations in the hot, dense plasma before any stars formed. Primordial black holes have not been confirmed, but they are a live topic in cosmology, partly because they are a candidate component of dark matter. If primordial black holes in a specific mass range formed in the early universe, they could account for some fraction of the dark matter observed today. The Laser Interferometer, Gravitational Wave Observatory, LIGO, has detected gravitational wave signals from merging black holes with mass distributions that are, in some cases, consistent with primordial black hole formation scenarios. The supermassive black hole formation problem has become significantly more acute in the last few years, thanks to the James Webb Space Telescope. JWST's extraordinary sensitivity at infrared wavelengths allows it to observe the most distant, and therefore the earliest, galaxies in the universe. And what it has found has surprised even optimistic cosmologists. Massive, luminous quasars, galaxies powered by actively accreting supermassive black holes, existing when the universe was less than 1 billion years old. Some appear to contain black holes with masses of hundreds of millions to over 1 billion solar masses, just 600 to 700 million years after the Big Bang. The problem is one of growth timescales. Gu, black hole, grows primarily by accreting surrounding matter. The fastest it can grow, the Eddington limit, beyond which radiation pressure from the hot accreting gas prevents further accretion, corresponds to a mass doubling time of roughly 40 to 50 million years. Starting from the largest plausible stellar mass black hole, perhaps 100 solar masses, formed from the direct collapse of the first generation of massive stars, growing at the Eddington limit continuously for the full billion years available, produces a black hole of approximately 10 to the 14th solar masses. That is more than enough. The observed supermassive black holes are smaller. But growing at the Eddington limit continuously is not realistic. Accretion is intermittent, regulated by feedback, and almost certainly sub-Eddington on average. With realistic accretion efficiencies, growing a billion solar mass black hole in 700 million years requires either starting from a very massive seed, perhaps 10,000 to 100,000 solar masses formed by direct collapse of gas clouds rather than stellar evolution, or a period of rapid super-Eddington accretion that is not fully understood. JWST is pushing the observational constraints on seed black hole mass and formation epoch in ways that existing models struggle to accommodate, and the origin of the first supermassive black holes remains one of the genuinely unsolved problems in astrophysics. The diversity of black hole formation mechanisms reflects a deeper point. Black holes are not a special, rare configuration of matter. They are the natural endpoint of extreme gravitational collapse, which is an expected outcome of the ordinary physics of stars and galaxies. Chapter 3: The Event Horizon. What crossing it means. The event horizon is one of the most conceptually difficult objects in physics because it is defined not by any local physical property, not by the presence of matter, not by a gradient in any measurable field, not by anything that could register on an instrument, but by a global property of space-time, the causal structure of the entire space-time manifold from the horizon to infinity. This global definition creates a profound observational asymmetry. An outside observer watching someone fall into a black hole never sees them cross the event horizon. As the infalling observer approaches the horizon, the light they emit takes progressively longer to climb out of the deepening gravitational well and reach the outside observer. The last signal emitted just outside the event horizon takes infinitely long to reach the outside. To the outside observer, the infalling object appears to slow down asymptotically, never quite reaching the horizon, becoming increasingly dim and redshifted as its light loses energy climbing the gravitational gradient. Eventually, the light from the infalling object is too dim and too redshifted to detect, and it effectively disappears. Not because it fell through, but because the outside observer can no longer receive any signals from the vicinity of the horizon. The infalling observer's experience is completely different. They pass through the event horizon in a finite proper time, the time measured on their own clock, without any local drama. The horizon is not a physical surface. Nothing special happens there in the local reference frame. The infalling observer continues inward, experiencing increasing tidal forces as the singularity approaches, until those tidal forces become sufficient to tear apart any physical object. A process called spaghettification, which is technically accurate and which planetary scientists named with uncharacteristic levity. The time between crossing the horizon and reaching the singularity is finite and, for stellar mass black holes, very short, milliseconds to seconds. There is a tool that physicists use to visualize this divergence clearly, and it is worth introducing because it will become important later. The Penrose diagram. A Penrose diagram is a two-dimensional map of an entire space-time, including, in principle, all of its infinite extent, compressed into a finite diagram by a mathematical transformation that preserves the causal structure. In a Penrose diagram, light rays always travel at 45 degrees, so the causal relationship between any two events, whether one can send a signal to the other is visually immediate. The Penrose diagram of a Schwarzschild black hole has a specific shape. The exterior universe occupies the right portion of the diagram, bounded on the upper left by a diagonal line representing the event horizon. The interior of the black hole is the triangular region above the event horizon, bounded at the top by a horizontal line representing the singularity. The infalling observer's world line, the path they trace through space-time, crosses the diagonal event horizon and then bends toward the horizontal singularity. No world line that crosses the event horizon can turn around and exit. Any path that crosses the diagonal horizon and subsequently points rightward toward the external universe would be pointing into the past, not the future, which is forbidden by causality. The Penrose diagram makes the one-way nature of the event horizon visually obvious. It also makes something else clear. The singularity is not a point in space at the center of the black hole. It is a boundary of space-time in the time direction, a future boundary that every infalling observer must reach, no matter what direction they try to move. Once inside, you cannot avoid the singularity any more than you can avoid tomorrow. The diagram also reveals the existence of an entirely separate region of space-time, a mirror image of the external universe connected to the physical universe through a wormhole or Einstein-Rosen bridge at the singularity of the eternal Schwarzschild solution. This second region is unreachable from our universe. It is causally disconnected. But its existence in the mathematical solution has inspired deep ideas about the relationship between entanglement and space-time geometry that became important in the context of the information paradox. This divergence of experience between the infalling observer and the outside observer is the first hint that black holes create profound paradoxes at the foundations of physics. The outside observer and the infalling observer have completely different pictures of what happens to matter falling into a black hole. The outside observer sees it slowed, red-shifted, and frozen at the horizon. The infalling observer passes through the horizon and continues to the singularity. Both descriptions are, within their respective reference frames, correct. The question of which one reflects the fundamental physical truth, what the state of the infalling matter really is, turns out to be one of the deepest unresolved questions in theoretical physics. There is a further subtlety about the event horizon that is rarely discussed in popular presentations. The event horizon is teleological. It depends on the entire future evolution of the space-time, not just on local conditions. Whether a given surface is an event horizon depends on whether signals emitted from just inside it can ever, at any time in the future, reach infinity. This is a global property that you cannot determine by any local measurement. If a black hole is growing, accreting mass, the event horizon expands as the mass increases. If the black hole is shrinking, evaporating as Hawking showed it must, the event horizon shrinks. The location of the event horizon at any given moment is defined by what happens to the black hole in the entire future, including the distant future. You cannot, in principle, locate the event horizon by measuring anything at a given time. This teleological character of the event horizon is one of the reasons that some physicists have argued for replacing it with a different concept, the apparent horizon, defined by local conditions. The apparent horizon is the surface at which light rays pointing outward are momentarily stationary rather than moving outward, where the inward pull of gravity exactly balances the outward propagation of light. For a stationary black hole, the apparent horizon coincides with the event horizon. For a dynamical black hole, one that is growing or evaporating, they diverge. The distinction matters for some of the deep problems in black hole physics. Chapter 4: Hawking Radiation, the discovery that changed everything. In 1974, Stephen Hawking published a paper in the journal Nature titled Black Hole Explosions, with a question mark that reflected his own initial disbelief at his result. The paper demonstrated, using a calculation that combined quantum field theory with the curved space-time of general relativity, that black holes are not perfectly black. They radiate. They emit a thermal spectrum of radiation, particles and photons, from just outside their event horizons, with a temperature inversely proportional to the black hole's mass. This radiation is now called Hawking radiation. The calculation that produced this result is subtle and beautiful. In quantum field theory, the vacuum of space-time is not truly empty. It is filled with vacuum fluctuations, the quantum equivalent of random noise, pairs of virtual particles that momentarily pop into existence and immediately annihilate each other before any physical measurement can detect them. This is not a metaphor or an approximation. It is a real, measurable effect. The Casimir effect, the measurable attractive force between two closely spaced, uncharged metal plates in vacuum, is a direct consequence of vacuum fluctuations and has been confirmed experimentally with high precision. Near the event horizon of a black hole, something unusual happens to these vacuum fluctuations. In the curved space-time near the horizon, pairs of virtual particles that form just outside the event horizon can be split. One particle falls inward past the horizon, the other escapes outward to infinity. The escaping particle is real. It carries real energy, and it is what constitutes Hawking radiation. The particle that falls inward carries negative energy in the local reference frame near the horizon, which effectively reduces the mass of the black hole. Over time, the black hole loses mass by this process. This is, admittedly, a simplified description of a calculation that is deeply technical. The rigorous version involves the behavior of quantum fields in curved spacetime, the definition of the vacuum state as seen by different observers, and the Bogoliubov transformation, a mathematical procedure relating the vacuum states defined by an observer at infinity to the vacuum states defined by an observer near the horizon. The result, however derived, is unambiguous. A black hole with a mass m radiates a thermal spectrum at the Hawking temperature T sub h equals h bar c cubed over 8 to pi g mk sub b, where h bar is the reduced Planck constant, c is the speed of light, g is the gravitational constant, and k sub b is Boltzmann's constant. The Hawking temperature for a solar mass black hole is approximately 60 nanokelvins, far colder than the cosmic microwave background radiation that fills the universe at 2.7 Kelvin. A solar mass black hole absorbs far more radiation from the CMB than it emits in Hawking radiation, so it is growing rather than evaporating in the current universe. But for a sufficiently small black hole, below about 10 to the 22nd kilograms, the mass at which the Hawking temperature equals the CMB temperature. Evaporation dominates, and the black hole loses mass. As it loses mass, its temperature rises, because temperature is inversely proportional to mass. As its temperature rises, it radiates more intensely. The evaporation accelerates. The black hole shrinks faster and faster, until, in the final stages, it is extraordinarily hot and radiating enormous energy. What Hawking called a black hole explosion, though it happens over an astronomical timescale for any macroscopic black hole. The evaporation timescale for a solar mass black hole is approximately 2 × 10⁻⁶ power years, incomprehensibly longer than the current age of the universe. This means that no stellar mass or supermassive black hole is in any danger of evaporating in any timescale that matters. But the theoretical result is what matters here, not the practical timescale. Hawking radiation was the first successful calculation in what physicists call semi-classical gravity, a regime in which gravity is treated classically, using general relativity. But the matter and fields in the gravitational background are treated quantum mechanically. This is not a complete theory of quantum gravity. It is an approximation that works in the regime where the space-time curvature is not too extreme. Outside the black hole, near the horizon, where general relativity gives a good description of the background geometry. It is not expected to be reliable near the singularity, where quantum gravity effects become important. Hawking radiation itself is a genuine prediction of the calculation, but it is also the source of the deepest crisis in fundamental physics. Chapter 5. The Information Paradox, the problem that broke physics. The information paradox begins with a question that sounds philosophical, but turns out to be physical, precise, and extraordinarily consequential. If you throw a book into a black hole, does the information in the book survive? To answer this, you need to understand what physicists mean by information. Information, in this context, is not just the readable text of the book. It is the complete quantum state of the system. The precise configuration of every particle, every quantum number, every degree of freedom that specifies the system completely. In quantum mechanics, the evolution of a physical system is governed by the Schrödinger equation, which has a specific property. It is unitary. Unitarity means that the evolution is reversible, that the complete quantum state at one time determines the complete quantum state at all other times, past and future. Information is conserved. It can change form, it can be scrambled beyond any practical ability to extract, but it is never fundamentally destroyed. This principle, the unitarity of quantum evolution, is one of the deepest and most fundamental postulates of quantum mechanics. It underpins the consistency of quantum theory. Now consider what happens to a book thrown into a black hole in light of Hawking's calculation. The black hole absorbs the book. It grows slightly. It continues to evaporate, emitting Hawking radiation. Eventually, after an astronomically long time, the black hole evaporates completely. It is gone. All that remains is the Hawking radiation it emitted over its lifetime. Hawking's original calculation suggested that Hawking radiation is precisely thermal, a featureless blackbody spectrum determined only by the black hole's temperature, which is determined only by its mass. Thermal radiation carries no information about what fell into the black hole. It is the physical equivalent of a completely scrambled signal from which the original message cannot be recovered, even in principle. If this is correct, if the Hawking radiation is truly featureless thermal radiation, then the information about the book is gone. Not merely scrambled, not merely inaccessible, but fundamentally destroyed. The complete quantum state that described the book before it fell and cannot be recovered from the Hawking radiation after the black hole evaporates. The evolution from book existing in the universe to Hawking radiation existing in the universe is not unitary. It violates the most fundamental postulate of quantum mechanics. This is the information paradox. It is not a minor technical detail. It is a flat contradiction between general relativity, which, combined with quantum field theory, predicts that Hawking radiation is thermal, and quantum mechanics, which requires that information is never destroyed. Both of these theories are extraordinarily well tested. Both appear to be fundamentally correct within their domains. They make, in the context of black hole evaporation, contradictory predictions about one of the most basic properties of physical evolution. This split, Hawking arguing for information loss, most of the physics community resisting it, defined the information paradox debate for 3 decades. And then in 2004, Hawking changed his mind. At the International Conference on General Relativity and Gravitation in Dublin, Hawking announced that he believed information was, in fact, preserved. The specific mechanism he proposed was that black holes, rather than having a single, definitive interior, were actually superpositions of many different, slightly different spacetimes, and that information was preserved in a subtle, scrambled form in these quantum superpositions. The argument was sketchy. He published a paper later that year that was criticized as incomplete by many colleagues. But the concession was significant. Hawking had bet Caltech physicist John Preskill a set of encyclopedias that information was destroyed in black holes. He lost the bet. He gave Preskill a baseball encyclopedia because, he explained, the information in it had been thoroughly scrambled. The concession was notable not because Hawking's 2004 argument was convincing. It largely wasn't, and the specific mechanism he proposed is not widely accepted, but because it reflected the broader shift in the physics community's consensus, driven by the ADS/CFT correspondence, which we will examine in detail in Chapter 8. The ADS/CFT result, published by Juan Maldacena in 1997, provided a framework in which black hole evaporation is manifestly unitary. Information is preserved, provably, in the dual description. This did not immediately explain how or where the information was encoded, but it made information destruction extremely implausible in the broader quantum gravity context. Hawking initially argued that the correct resolution was that information is genuinely destroyed in black holes, that the unitarity of quantum mechanics was simply violated in this context, and that black holes represent an exception to quantum mechanical evolution. This was an extraordinarily radical position. It implied that quantum mechanics was not a fundamental theory, but an approximation that breaks down in the presence of black holes. Most physicists were not willing to accept this. The alternative? That information is somehow preserved, that the Hawking radiation is not exactly thermal, but contains subtle correlations encoding the quantum state of everything that fell into The black hole requires explaining how information gets out of the black hole. The event horizon is a one-way membrane. Nothing crosses it from inside to outside. How can information that is inside the event horizon end up encoded in radiation emitted from outside? This seems to require either a violation of general relativity's prediction that nothing escapes the horizon, or some exotic mechanism by which information is copied, present both inside the black hole and in the Hawking radiation, which would violate a different principle of quantum mechanics called the no-cloning theorem. This three-way tension between information preservation, unitarity, the one-way nature of the event horizon from GR, and no copying of quantum information from the no-cloning theorem is what makes the information paradox genuinely hard. It is not a problem that can be solved by being cleverer within the existing frameworks. It requires, in some sense, that one of the existing frameworks is wrong or incomplete in a way that becomes important near black holes. Chapter 6: Black Hole Thermodynamics. The 4 laws that shouldn't exist. Before reaching the most recent developments in the information paradox, we need to establish the framework of black hole thermodynamics. Because the information paradox becomes far more precise and far more tractable once you understand that black holes are not just dark gravitational objects, but fully thermodynamic systems with temperature, entropy, and all the machinery of statistical mechanics. The thermodynamics of black holes emerged from a series of insights in the early 1970s from Jacob Bekenstein, Brandon Carter, James Bardeen, and Hawking himself. Bekenstein, then a graduate student at Princeton, proposed in 1972 that black holes must have entropy, a measure of disorder, or more precisely, of missing information, proportional to the area of their event horizons. This was a deeply radical proposal for several reasons. First, it suggested that a black hole, an object that appears featureless to an outside observer, characterized entirely by its mass, charge, and spin, has an enormous amount of hidden internal entropy. The Bekenstein-Hawking entropy is SBH equals Ka over 4Lp squared, where K is Boltzmann's constant, A is the area of the event horizon, and L sub p is the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. For a solar mass black hole, this entropy is approximately 10 to the power of 77, roughly the number of microstates consistent with the black hole's macroscopic properties. For comparison, the entropy of the entire Sun as a star is approximately 10 to the power of 57. A solar mass black hole has about 10 to the power of 20 times the entropy of the Sun from which it might have formed. This is one of the deepest facts about black holes, and its implications are still being worked out. If a black hole has entropy, and entropy measures the number of microscopic configurations consistent with the macroscopic state, then the question becomes, what are those microstates? What degrees of freedom are being counted? A black hole, by the no-hair theorem, the result that black holes are entirely characterized by their mass, charge, and spin, appears to have no internal structure to count microstates over. Where is the entropy stored? This question, the microscopic origin of black hole entropy, is one of the litmus tests for any proposed theory of quantum gravity. String theory in 1996 provided the first successful microscopic derivation of black hole entropy. For a specific class of extremal black holes with the maximum possible charge for their mass, Kumrun Vafa and Andrew Strominger at Harvard showed that the number of string-theoretic microstates consistent with the black hole's macroscopic properties exactly matches the Bekenstein-Hawking formula. This was a major success for string theory, but it was for a highly idealized, non-realistic class of black holes, and the extension to realistic Schwarzschild black holes remains incomplete. The 4 laws of black hole thermodynamics, proposed by Bardeen, Carter, and Hawking in 1973, are precise analogues of the 4 laws of ordinary thermodynamics, with the surface gravity of the black hole playing the role of temperature and the event horizon area playing the role of entropy. The 0th law states that the surface gravity is constant over the horizon of a stationary black hole. In analogy with the 0th law of thermodynamics, temperature is uniform in thermal equilibrium. The 1st law relates changes in the black hole's mass to changes in its area and angular momentum, in analogy with conservation of energy. The 2nd law, the most important, states that the total area of all event horizons never decreases, in analogy with the thermodynamic statement that total entropy never decreases. The 2nd law of black hole thermodynamics is an exact consequence of general relativity and the assumption that energy is positive. It was proved by Hawking as a theorem about space-time geometry, without any reference to thermodynamics. The fact that it turned out to be a direct analog of the thermodynamic 2nd law was initially thought to be a mathematical coincidence. Bekenstein's proposal that it was not a coincidence, that the event horizon area was literally entropy, was initially dismissed by Hawking and others on the grounds that entropy implies temperature. And black holes are perfectly black and therefore cannot have a temperature. Hawking radiation resolved this circularity. When Hawking showed that black holes do have a temperature, the Hawking temperature, the entire thermodynamic framework snapped into place. The analogy was not a coincidence. Black holes are genuine thermodynamic objects. Their entropy is real. Their temperature is real. The 4 laws of black hole thermodynamics are not analogies of thermodynamics. They are thermodynamics, applied to the geometry of space-time. This is beautiful, but deeply puzzling. Thermodynamics emerges from statistical mechanics, from the averaging over enormous numbers of microscopic degrees of freedom. Black hole thermodynamics demands that black holes have an enormous number of microscopic degrees of freedom counted by the Bekenstein-Hawking entropy, but those degrees of freedom are invisible to general relativity, which describes the black hole as a smooth, featureless geometry. Whatever the microscopic theory of quantum gravity is, it must contain degrees of freedom that, when counted, reproduce exactly the Bekenstein-Hawking entropy. And it must do so in a way that also explains how information that falls into a black hole can be encoded in those degrees of freedom and eventually escape in the Hawking radiation. Chapter 7: The Firewall Paradox. When the problem gets worse. For 30 years after Hawking's 1974 paper, the information paradox was a serious theoretical problem that motivated a lot of work but had no clear resolution. In 2012, it became significantly worse. In a paper published in the Journal of High Energy Physics, 4 physicists, Ahmed Al-Maheri, Donald Marolf, Joseph Polchinski, and James Sully, published a result known by the acronym APS after their initials, and by the colloquial title of the firewall paradox. Their argument is one of the most devastating in theoretical physics, and it proceeds as follows. Assume that black holes do not destroy information, that the Hawking radiation from a black hole is, in principle, unitary, meaning it carries encoded information about everything that fell into the black hole. This is the mainstream position that most physicists had converged on after the development of the ADS/CFT correspondence, which we will discuss shortly. Unitarity means that the Hawking radiation emitted in the later stages of black hole evaporation must be entangled with the early Hawking radiation. The correlations between early and late radiation are what encode the information. Now consider a specific situation. An observer, call her Alice, is outside the black hole, collecting the early Hawking radiation. Another observer, call him Bob, is falling into the black hole. At the moment Bob crosses the event horizon, he passes through the same region of space that will, at a much later time, be emitting the Hawking radiation that Alice collects. The late Hawking radiation that Alice collects must be entangled with the early Hawking radiation for unitarity. But it must also be entangled with the interior modes that Bob observes as he crosses the horizon, for Bob's experience to be smooth and unremarkable at the horizon as general relativity demands. But quantum mechanics has a rule called monogamy of entanglement. A quantum system cannot be maximally entangled with two different systems simultaneously. If the late Hawking radiation is maximally entangled with the early Hawking radiation, it cannot also be maximally entangled with the interior modes near the horizon. Something has to give. OMPS argued that the resolution is that the entanglement between the late radiation and the interior modes is broken, and the physical consequence of breaking that entanglement is dramatic. The vacuum of quantum field theory near the horizon, which normally appears smooth and empty to an infalling observer, instead contains a highly energetic collection of quanta, a firewall of radiation at the event horizon that would incinerate any infalling observer at the moment they crossed. The smooth horizon of general relativity is replaced by a wall of fire. This is an extraordinary conclusion. It says that if information is preserved, which unitarity requires, then general relativity is violated at the event horizon, in a regime where general relativity should be perfectly accurate. The black hole's interior is destroyed. Bob burns up at the horizon, rather than falling through smoothly. The principle of equivalence, the cornerstone of general relativity, the statement that freely falling observers feel no local gravitational effects, is violated in a spectacular and violent way. The AMPS paper presented physics with a trilemma. Either information is destroyed, violating quantum mechanics, or the horizon is smooth, violating unitarity, or there is some other resolution that modifies our understanding of quantum mechanics, general relativity, or both. None of the options is acceptable within the existing theoretical framework. The firewall paradox sharpened the information paradox from a theoretical puzzle to an acute crisis. The firewall paradox generated an enormous response in the theoretical physics community. Hundreds of papers were written in the following years, proposing possible resolutions. Some proposed that the paradox reveals a breakdown of the standard framework for comparing observations made in very different reference frames a proposal called black hole complementarity, originally developed by Leonard Susskind and Gerard 't Hooft, and refined in response to AMPS. Some proposed that the interior of a black hole is somehow encoded in the exterior, that the degrees of freedom behind the horizon are not additional degrees of freedom, but are the same degrees of freedom seen from a different perspective, a concept called ER equals EPR, proposed by Juan Maldacena and Leonard Susskind in 2013. Some proposed that the correct description of the black hole interior requires abandoning the local geometric picture of space-time near the horizon and replacing it with something radically different. None of these proposals achieved consensus. The information paradox and the firewall paradox remained unresolved, the central open problem in theoretical physics, until a development in 2019 that has, tentatively and partially, begun to point toward an answer. Chapter 8. A DS/CFT, the duality that changed the game. In November 1997, a 28-year-old Argentine-American physicist named Juan Maldacena posted a paper to the physics preprint server that would become the most cited paper in the history of theoretical physics. It is titled "The Large N-Limit of Superconformal Field Theories and Supergravity," which is not a title designed to communicate its significance to a general audience. What it contains is a conjecture, now strongly supported by overwhelming evidence, even if not formally proved, that has restructured the entire landscape of quantum gravity research and provided the framework within which the information paradox is now most productively investigated. The conjecture, now called the ADS/CFT correspondence, or the holographic duality, states the following. A theory of quantum gravity in a negatively curved spacetime, called anti-de Sitter space, is exactly equivalent, identical in every physical prediction, to a specific kind of quantum field, theory without gravity, defined on the lower dimensional boundary of that spacetime. The two descriptions, quantum gravity in the bulk spacetime and quantum field theory on the boundary, are dual. They describe the same physics from two different perspectives, and any calculation you can do in one description can in principle be done in the other. To make this concrete, the specific original example Maldacena considered was type 2 B-string theory in 5-dimensional anti-de Sitter space times a 5-dimensional sphere, which is dual to a specific quantum field theory called N equals 4 super Yang-Mills theory, living on the 4-dimensional boundary of the ADS space. The boundary theory has no gravity. It is an ordinary quantum field theory, fully unitary, in which information is manifestly conserved. Because the two descriptions are equivalent, the gravity theory in the bulk must also be unitary. Information is preserved in black hole evaporation because the dual boundary description is a standard quantum field theory, and standard quantum field theories conserve information. This is the result that shifted the consensus on the information paradox. Maldacena's conjecture does not explain how information gets out of a black hole. It does not identify the mechanism by which the Hawking radiation is non-thermal and encodes information about the infalling matter. But it establishes, in the framework of the strongest available theoretical tool for studying quantum gravity, that information must be preserved. The question changed from, is information preserved, to how is information preserved? The ADS/CFT correspondence has a second implication that is equally important and somewhat harder to grasp. It is holographic. The bulk space-time has one more dimension than the boundary theory. All the information about the three-dimensional bulk, including all the gravitational degrees of freedom, all the matter fields, all the black holes, is encoded in the two-dimensional boundary. The boundary is not just a convenient mathematical device, it is a complete, equivalent description of the bulk physics. The interior of the spacetime is, in a precise sense, encoded in the boundary. This holographic principle, proposed earlier by T. Hooft and Susskind on the basis of black hole entropy arguments, says something radical about the nature of spacetime itself. The three-dimensional interior is not more real than the two-dimensional boundary. Spacetime, at least in the anti-de Sitter context, is emergent. It is a derived concept, not a fundamental one. The degrees of freedom of the boundary theory, organized in a specific way, produce the appearance of a bulk spacetime with one more dimension. The third dimension of space, from this perspective, is not a fundamental ingredient of reality, but an emergent structure arising from the organization of quantum information on the boundary. Before the implications, it is worth pausing on what holographic actually means in a physical rather than a mathematical sense, because it is one of the most conceptually radical things that theoretical physics has ever said. The original hologram, the optical one, made with lasers, works by recording not just the intensity of light reflected from an object, but the full phase information of the wave field. When you illuminate the holographic plate with a laser, the full three-dimensional scene reconstructs itself. All the information about the three-dimensional object is encoded in the two-dimensional plate, not approximately encoded, completely encoded. Every depth Q, every parallax shift, every shadow. The ADS/CFT holographic duality is analogous but more radical. In optical holography, the three-dimensional object is physically real, and the two-dimensional plate is an encoding of it. In ADS/CFT, neither description is more fundamental than the other. The three-dimensional bulk spacetime and the two-dimensional boundary theory are two equally valid descriptions of the same physical reality. There is no fact of the matter about which is really three-dimensional. You can work in whichever description is more convenient for the question you're asking. The three-dimensional interior, including all its gravitational dynamics, all its black holes, all its geometry, is not more real than the two-dimensional boundary quantum field theory that encodes it. More recent work in quantum information theory has made this holographic relationship even more precise. The Ryu-Takayanagi formula, proved by Shinsei Ryu and Tadashi Takayanagi in 2006, in the context of ADS/CFT, states that the entanglement entropy of a region of the boundary theory is proportional to the area of a minimal surface in the bulk spacetime that has the same boundary. This is a precise quantitative relationship between the entanglement structure of the boundary quantum state and the geometric structure of the bulk spacetime. In the appropriate limit, the Ryu-Takayanagi formula reduces to the Bekenstein-Hawking entropy formula for black holes. The deeper implication is that the geometry of spacetime, the metric, the distances between points, the curvature, is encoded in the entanglement structure of the boundary quantum state. more entanglement between two regions of the boundary corresponds to more connectivity between the corresponding regions of the bulk. Less entanglement corresponds to less geometric connectivity. This led the physicist Mark van Ramsdonk in a 2010 paper to propose the evocative idea that space-time is built from entanglement, that the connectedness of the space-time geometry is literally determined by the pattern of quantum entanglement in the boundary theory, and that cutting the entanglement would cause the geometry to fall apart. This is a precise statement, not a metaphor. It has been formalized in terms of tensor networks, mathematical structures from quantum information theory that, when arranged in specific patterns, reproduce the Ryu-Takayanagi formula and the holographic relationship between entanglement and geometry. The tensor network picture of holography is now a productive research program that connects quantum error correction, quantum information theory, and quantum gravity in unexpected ways. The implications are dizzying. If space-time is emergent, if three-dimensional space is a derived structure rather than a fundamental one, then the familiar picture of a black hole as a region of space-time with an interior and an event horizon may not be the deepest description. There may be a more fundamental description in terms of quantum information on the boundary, in which the interior of a black hole is not a separate, isolated region, but is encoded in the same degrees of freedom as the exterior. The event horizon, from this perspective, is not a fundamental barrier, but a feature of an approximate, effective description that breaks down when you look closely enough at the quantum information structure. This is the conceptual backdrop against which the developments of 2019, the developments that represent the most significant recent progress on the information paradox, need to be understood. Chapter 9, the page curve and the island formula. A partial resolution. In 1993, the physicist Don Page published a paper calculating what the entropy of the Hawking radiation from an evaporating black hole should look like as a function of time if information is preserved. If you consider the black hole and its Hawking radiation as a combined system, and if you calculate the entropy of the radiation subsystem alone, the result depends on whether information is lost or preserved. Hawking's original thermal calculation gives an answer that increases monotonically. The entropy of the radiation increases continuously as the black hole evaporates, because each new thermal photon added to the radiation is independent of all the others, adding its maximum possible entropy. The entropy rises and keeps rising until the black hole has completely evaporated and the total entropy is at its maximum. Page showed that if information is preserved, the entropy of the radiation must behave differently. It should rise initially, in the early stages of evaporation, when the Hawking radiation is highly mixed and has not yet accumulated enough correlations to encode information. But at a specific moment, called the Page time, approximately halfway through the evaporation process in terms of the number of particles emitted, the entropy should start decreasing. As the black hole evaporates further and the correlations build up in the radiation becomes more and more pure, more and more like an exact, unitary transformation of the initial state. The entropy falls until, at the end of evaporation, the radiation is in a pure quantum state with zero entropy, consistent with having all the information of the infalling matter encoded within it. The Page curve, the entropy of the radiation as a function of time, rising then falling in a characteristic arch, is a precise prediction of unitarity. It is not a computation from first principles. It is a consequence of the general properties of quantum mechanics applied to a system that evaporates unitarily. Any complete quantum gravitational description of black hole evaporation must reproduce the Page curve. For decades after Page's 1993 paper, there was no mechanism for reproducing the Page curve from first principles gravity calculations. Hawking's semi-classical calculation gives the monotonically rising entropy, the wrong answer. The Page curve requires quantum gravitational corrections that go beyond the semi-classical approximation in a regime near the end of the evaporation, where quantum gravity is important and where the semi-classical approximation is expected to break down. Then, in 2019, a series of papers by Ahmed Almhairi, Netta Engelhardt, Donald Maroff, Henry Maxfield, and Jeff Pennington derived the Page curve from a first principles gravity calculation using a specific technique called the island formula. The key insight is subtle and remarkable. When you calculate the entropy of the Hawking radiation using the Euclidean path integral, a technique in which you analytically continue the time coordinate to imaginary values and compute quantum amplitudes as path integrals over Euclidean geometries, you are summing over all possible spacetime geometries that contribute to the amplitude. In the early phase of evaporation, the dominant contributions come from smooth, connected geometries, the standard semi-classical spacetime. But in the later phase, there is an additional class of geometries that become important. Geometries in which the interior of the black hole, the region behind the event horizon, is connected through a non-trivial topological handle to the external region, where the radiation is collected. These additional geometries are called saddle points or replica wormholes, and their contribution to the entropy calculation changes the result precisely at the Page time. Including replica wormhole contributions, the entropy of the radiation rises to the Page time and then decreases, exactly as Page's information theoretic argument requires. The Page curve is reproduced from a gravitational calculation. The island formula, which encapsulates the result in a specific prescription, says the following. To compute the entropy of the radiation, you should include, in addition to the radiation region, an island, a region inside the black hole that is identified with the radiation for the purpose of the entropy calculation. The entropy of the radiation plus its island, minimized over all possible island choices, gives the correct answer. Early in the evaporation, the optimal island has zero area and the entropy rises. After the Page time, there is an island inside the black hole that significantly reduces the computed entropy, and including this island gives the decreasing part of the Page curve. The island formula is one of the most significant results in theoretical physics of the last decade. It demonstrates that a gravitational calculation, path integral over geometries, including the topologically non-trivial saddle points, reproduces the expected unitary behavior. It does not completely solve the information paradox. It does not provide a precise microscopic mechanism for how information escapes, and the derivation involves approximations that are not fully controlled in all regimes. But it shows, in a framework derived from first principles gravity, that the entropy of the Hawking radiation follows the page curve rather than the monotonically increasing curve of Hawking's original calculation. The replica wormholes that drive this result are a striking physical interpretation. They represent contributions in which two copies of the spacetime, made in the replica trick of the entropy calculation, are connected through the black hole interior. The black hole interior is, in this description, a kind of bridge between the early and late radiation, creating the correlations that allow information to be encoded in the Hawking radiation. The wormhole is not a traversable connection. You cannot use it to send information between the early and late radiation in the classical sense. But its presence in the quantum gravitational path, integral, is what makes the entropy calculation come out right. This connects back to the ER equals EPR proposal of Maldacena and Susskind. Entanglement between the early and late Hawking radiation is, in the gravitational description, geometrically realized as a wormhole connecting the interior of the black hole to the exterior. The entanglement structure of the quantum state and the geometric structure of the spacetime are two descriptions of the same thing. This is a precise version of the holographic principle in action. The geometric structure of the interior of the black hole is encoded in the quantum information structure of the exterior radiation. The replica wormhole result raises a further question that is both fascinating and disturbing. What does it mean for the black hole interior? If the information about everything that fell into the black hole is encoded in the Hawking radiation, as the page curve and island formula imply, then the black hole interior is not an independent, separate region of spacetime. It is, in some sense, redundant. All the information it contains is already present in the exterior radiation. The interior degrees of freedom are not additional degrees of freedom on top of the exterior ones. They are the same degrees of freedom, encoded in a different way. This interpretation, sometimes called interior reconstruction, is one of the most radical ideas in modern theoretical physics. It says that what appears from the perspective of an infalling observer to be a spacious interior region full of matter and fields is actually a description of the same quantum state that, from the perspective of an outside observer, looks like Hawking radiation. The two descriptions are complementary in a precise technical sense. They cannot both be made precise simultaneously, because making both precise would violate the no-cloning theorem. This is the resolution of the duplication problem. You cannot simultaneously have both the information in the interior and the same information in the exterior, because the quantum mechanical framework forbids it. The two descriptions are not simultaneous alternatives, but complementary aspects of a single quantum state. The specific mechanism by which interior information is encoded in the exterior radiation is related to the replica wormholes. After the page time, the dominant contribution to the path integral includes geometries in which the interior is connected to the exterior radiation through Euclidean wormholes, and the interior is literally identified with a portion of the exterior in the calculation. The interior island that appears in the island formula is not a separate region. It is identified with the radiation region in a specific quantum gravitational sense. This is an extraordinary picture. It says that the space-time inside a black hole, the region that, classically, is completely cut off from the outside. Is, in the quantum gravitational description, not cut off at all. It is the same region seen from a different angle of the quantum information structure. The interior and exterior are not genuinely distinct regions in the quantum gravitational sense. They are two perspectives on the same quantum state. Whether this means the firewall paradox is resolved, whether Bob falling into the black hole really does experience a smooth horizon rather than a wall of fire, depends on subtleties about what interior reconstruction means for the local physics experienced by infalling observers. This is still being worked out, but the direction of the answer is becoming clearer. The interior is encoded in the exterior. The singularity may be resolved by quantum gravity, and the information that fell in comes back out in the Hawking radiation, scrambled beyond any practical decoding, but not fundamentally destroyed. The 2019 Island Formula papers have not resolved every aspect of the information paradox. The firewall paradox, in particular, has not been definitively laid to rest, and there are still deep questions about what happens at the endpoint of black hole evaporation and about the precise nature of the semi-classical approximations involved. But they represent the most substantial progress toward a resolution in the 45 years since Hawking's original 1974 calculation, and the direction they point toward emergent space-time, toward the geometric interpretation of quantum entanglement, toward the holographic encoding of black hole interiors, is widely considered to be the right direction. Chapter 10: Gravitational Waves. Hearing black holes for the first time. On September 14th, 2015, at 5:51 a.m. Eastern Time, both detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, simultaneously registered a brief distortion in the length of their measurement arms, lasting approximately 0.2 seconds, with a peak amplitude equivalent to a fractional length change of about 10 to the power of -21. The signal was a chirp, a rising frequency sweep, starting at about 35 Hz and sweeping to approximately 150 Hz in the final tenth of a second before it ended. This signal, designated GW150914 for the date of its detection, was the first direct detection of gravitational waves. It took almost exactly 100 years from Einstein's prediction of their existence in 1916 to their first observation. The Nobel Prize in Physics 2017 was awarded to Kip Thorne, Rainer Weiss, and Barry Barish for the detection. But what caused it? The answer, determined by comparison with the predictions of general relativity for different sources, is two black holes, one with a mass of approximately 29 solar masses, the other approximately 36 solar masses, spiraling toward each other at velocities approaching the speed of light, merging into a single black hole of approximately 62 solar masses in a fraction of a second. The difference, 29 plus 36 equals 65 solar masses in, 62 solar masses out, represents 3 solar masses of energy, approximately 5 times 10 to the 47th power joules, radiated away in gravitational waves in about 1 second. For that brief period, this system was radiating energy at a rate 50 times greater than the combined light output of every star in the observable universe. that 0.2-second chirp, barely distinguishable from noise in the detector data, was the sound of two objects the size of a city, each with the mass of tens of suns, merging at half the speed of light. The fact that we could detect it at all, from a distance of approximately 1.3 billion light-years, reflects the extraordinary sensitivity of the LIGO instruments. LIGO measures length changes using laser interferometry across arms 4 kilometers long. The arm length change at peak signal was approximately 4 times 10 to the minus 18 meters, less than 1,000th the diameter of a proton. Since GW 150914, LIGO, along with its partner detectors Virgo in Italy and Kagra in Japan, has detected over 100 gravitational wave events, the vast majority from binary black hole mergers. The population of detected binary black hole systems has revealed a distribution of black hole masses that was not anticipated by stellar evolution models. There are mergers involving black holes in the mass range of 50 to 100 solar masses, the pair instability mass gap, where stellar evolution theory predicts that black holes cannot form directly by stellar collapse because stars in this mass range are disrupted by runaway pair production in their cores before they can collapse. The presence of objects in the pair instability gap in the LIGO catalog suggests either a second generation of mergers, previous mergers producing larger black holes that then merge again, or formation pathways such as primordial black holes, or dynamical formation in dense stellar clusters that do not go through conventional stellar collapse. Gravitational wave astronomy has also resolved a question that optical astronomy never could: the mass distribution and spin properties of black holes. Spinning black holes, the general Kerr solution of Einstein's equations, which describes a rotating black hole, have an event horizon structure more complex than the Schwarzschild, non-rotating case. The Kerr black hole has 2 horizons: an outer event horizon, analogous to the Schwarzschild horizon, and an inner Cauchy horizon, inside which the predictability of classical general relativity breaks down. Between the 2 horizons lies the ergosphere, a region where space-time itself is dragged around the rotating black hole, making it impossible for any observer to remain stationary with respect to the distant stars. Inside the ergosphere, but outside the event horizon, energy can in principle be extracted from the rotating black hole through the Penrose process. A particle falling into the ergosphere can split into 2, with one fragment falling into the black hole and the other escaping, with more energy than the original particle carried. The rotational energy of the black hole is reduced in the process. The spin of the black holes, detected by LIGO, has been measured from the gravitational waveform. The spin affects the rate at which the 2 black holes spiral together, imprinting characteristic signatures on the chirp. The distribution of detected spins has implications for black hole formation channels and has revealed that many of the detected black holes are merging with small or random relative spin orientations, consistent with dynamical formation in dense environments like globular clusters, rather than formation from co-evolving binary star systems. The catalog of gravitational wave events has also given us the first observed example of a neutron star merger, GW 170817, detected on August 17, 2017, produced simultaneously with a gamma-ray burst detected by the Fermi telescope just 1.7 seconds after the gravitational wave signal. The near simultaneous detection of gravitational waves and light from the same event confirmed to extraordinary precision that gravitational waves travel at the speed of light. Their arrival times differed by 1.7 seconds across a travel distance of approximately 130 million light-years. This placed the tightest constraint ever on any deviation between the speed of gravity and the speed of light. The fractional difference is less than 1 part in 10 to the 15th power. Entire classes of modified gravity, theories that had been proposed as alternatives to general relativity to explain the accelerating expansion of the universe without dark energy, predict measurable deviations in this speed ratio, and GW 170817 eliminated them in a single observation. The merger of two neutron stars in GW 170817 also produced the first confirmed kilonova, the R-process nucleosynthesis event, in which the collision of neutron-rich matter creates heavy elements. The optical emission from the GW 170817 kilonova was detected by dozens of ground and space-based observatories in the weeks following the merger, and the spectroscopic identification of strontium, gold, platinum, and other heavy elements confirmed that neutron star mergers are a primary production site for roughly half the elements heavier than iron in the universe. Every gold ring on Earth is assembled from material forged in the collision of neutron stars, detected in events like GW 170817, distributed through galaxies by subsequent stellar processes. Gravitational wave astronomy, in establishing this connection, answered one of the longest-standing questions in nuclear astrophysics. Whether the final product of a neutron-star merger is a black hole is itself a question that gravitational waves can answer. The ring-down signal, the oscillation of the merged object as it settles into its final stationary state, carries a signature that distinguishes a neutron star remnant from a black hole, and future gravitational wave detectors, with improved sensitivity in the high-frequency range, are expected to resolve this question for future events. Each gravitational wave event is, in a precise sense, a controlled experiment in the regime of extreme gravity. Two objects at the event horizon scale colliding at relativistic velocities. The match between the observed waveforms and the predictions of general relativity, computed using numerical relativity codes that solve Einstein's field equations on supercomputers, is extraordinary. General relativity, untested in the strong field, dynamical regime before 2015, has passed every test that gravitational wave observations have subjected it to. There is no sign of a deviation from the predictions of classical general relativity in the observed waveforms at any level of precision currently achievable. Whatever quantum gravity eventually looks like, it must reduce to classical general relativity in the semi-classical, limit to precision at least as good as the current LIGO measurement uncertainties. Chapter 11. What we saw when we actually looked, the EHT images. The Event Horizon Telescope is not a single instrument. It is a network, a very long baseline interferometry array that links radio telescopes across the globe to form a virtual telescope with a baseline equal to the diameter of the Earth. The technique works by recording the radio waves from the target source simultaneously at each telescope, along with extremely precise timing information from hydrogen mass or atomic clocks, and then combining the data in post-processing to extract the interference pattern that would have been produced by a single telescope the size of the Earth. The angular resolution of a telescope is determined by the ratio of the wavelength of light being observed to the diameter of the telescope aperture. For the EHT, operating at a wavelength of 1.3 millimeters, and with a baseline of approximately 10,000 kilometers, the angular resolution is approximately 20 to 40 micro-arc seconds. Fine enough, for the first time in human history, to resolve the event horizon scale shadows of specific known black holes. The EHT targeted two black holes, M87 star, the supermassive black hole at the center of the Messier 87 galaxy, 55 million light-years away, with a mass of approximately 6.5 billion solar masses, and SGR-A star, the supermassive black hole at the center of our own Milky Way galaxy, 26,000 light-years away, with a mass of approximately 4 million solar masses. The image of M87 star, released in April 2019, showed what theorists had predicted, but never directly confirmed: a bright ring of emission surrounding a dark central shadow. The ring is produced by hot plasma, gas heated to billions of degrees, orbiting the black hole, and, in the region closest to the event horizon, being deflected and captured by the black hole's gravity. The bright ring is a combination of direct emission and gravitationally lensed emission. Light that has been bent by the black hole's gravity through large angles before reaching Earth. The shadow is the projection of the photon sphere, the region where photons follow circular orbits around the black hole, and its size and shape provide direct information about the mass and spin of the black hole. The size of the shadow is determined by the Schwarzschild radius and the distance to the black hole. For M87 star, the event horizon angular diameter is approximately 40 micro-arc seconds, right at the edge of EHT's resolution. The shadow is slightly larger because the apparent shadow boundary corresponds to the photon capture orbit, not the event horizon itself, a subtlety that encodes a specific prediction of general relativity. The observed shadow size is consistent with the black hole mass of 6.5 billion solar masses independently estimated from stellar kinematics. The second EHT target, SGR-A star, presented a more challenging imaging problem. Although SGR-A star is vastly closer than M87 star, 26,000 light-years versus 55 million, its much smaller mass means its event horizon is smaller in angular size, and more importantly, the plasma around SGR-A star orbits on a much shorter timescale. For M87 star, the orbital period of material near the event horizon is several days, long enough that the structure of the emission ring is essentially static over the time span of an observing campaign. For SGR-A star, the orbital period is only tens of minutes. The emission structure changes significantly during a single night of observation, creating a blurring effect that requires sophisticated analysis techniques to handle. The EHT released the first image of SGR-A star in May 2022, showing the same bright ring and dark shadow morphology as M87 star, but with a ring that is less sharply defined due to the rapid variability. Both images confirmed the existence of the photon ring, a feature specific to the strong gravity regime of general relativity, with no Newtonian equivalent. and both are consistent with the predictions of general relativity for rotating, Kerr, black holes with the independently measured masses. The images are, in the most literal sense, photographs of the boundary between what we can see and what we cannot. The shadow is not merely a region of low brightness. It is the visual signature of the event horizon, the boundary of the causally disconnected region from which no light escapes. What the images do not show, and cannot show, is anything about the interior. The shadow boundary traces the photon capture orbit, not the event horizon itself. The event horizon is inside the shadow. Nothing that happens inside the event horizon affects what the EHT sees. The image is the most direct visual evidence for the existence of black holes ever obtained, and it is entirely consistent with general relativity. But it cannot resolve the information paradox, the firewall paradox, or any of the questions about what happens to matter once it crosses the horizon. Those questions lie permanently on the other side of the shadow. The EHT collaboration's ongoing work includes higher resolution imaging at shorter wavelengths, observing at 0.87 millimeters rather than 1.3 millimeters, which increases the angular resolution by 50%, and the addition of new telescopes to the array, including space-based telescopes that would increase the baseline beyond the Earth's diameter and further improve resolution. Future EHT observations are expected to resolve the photon ring structure in detail, providing a precise test of the Kerr metric, the exact space-time geometry around a rotating black hole in the regime of maximum curvature. Chapter 12, The Singularity, where physics actually breaks. We have been circling the singularity throughout this entire video, mentioning it as the terminus of infalling matter and the location where the known laws of physics break down. It is time to look at it directly. The singularity at the center of a Schwarzschild black hole, or more precisely, at the future boundary of the Schwarzschild interior in the Penrose diagram, is a point at which the curvature of spacetime becomes infinite. The Riemann curvature tensor, which measures the intrinsic curvature of spacetime and which determines the tidal forces experienced by infalling observers, diverges as you approach the singularity. Tidal forces become infinite. The proper time to reach the singularity from the event horizon is finite and unavoidable, but as you approach it, the gradient of gravity across your body becomes infinite, stretching you in the radial direction and compressing you in the transverse directions without limit. This is spaghettification without a soft landing, a divergence, not merely a large number. A divergence in a physical theory is not a description of a physical phenomenon. It is a flag. The theory is being pushed outside its domain of validity. The singularity at the center of a black hole is not a prediction that anything physical actually becomes infinite. It is a prediction that general relativity breaks down, that the theory needs to be replaced by something that does not produce infinities at these length and energy scales. That replacement theory is quantum gravity, and in quantum gravity, the singularity is expected to be resolved, replaced by something finite, something physical, something that the laws of physics can describe. What that replacement looks like depends on the specific theory of quantum gravity. In loop quantum cosmology, a cosmological application of loop quantum gravity, which quantizes space-time itself by replacing the smooth continuum of general relativity with a discrete network of spin states. The Big Bang singularity at the origin of the universe is replaced by a big bounce, in which a previous contracting phase of the universe reaches a maximum density set by the Planck density and rebounds into the current expanding phase. An analogous mechanism in loop quantum gravity applied to black holes would replace the black hole singularity with a region of maximum density from which the interior bounces, potentially into a new region of space-time, sometimes called a Planck star picture, in which the black hole's interior bounces at the Planck scale and re-expands, eventually exploding out through what had been the event horizon. In string theory, the singularity is expected to be resolved by the extended nature of strings. The fundamental objects of string theory are not point particles, but one-dimensional extended objects, and the maximum curvature that a string can probe is set by the string scale, typically somewhat larger than the Planck scale. At sufficiently high curvature, the string's extended nature smears out the singularity, replacing the infinite curvature with a finite maximum. The precise form of the resolution depends on the specific string background and is an active area of research. It is worth pausing on exactly what the singularity theorems prove, because they are among the most important results in mathematical physics, and they are often misunderstood. Roger Penrose proved the first singularity theorem in 1965, a result for which he was awarded the Nobel Prize in Physics in 2020, shared with Andrea Ghez and Reinhard Genzel for the observational confirmation of the black hole at the center of the Milky Way. Penrose's theorem states that if a trapped surface exists, a surface from which all light rays converge inward rather than diverging outward, then a singularity is inevitable under the assumption that the energy density is everywhere non-negative, the energy condition. The theorem does not require any symmetry assumption. It does not assume spherical symmetry or any particular distribution of matter. It says, given a trapped surface, given non-negative energy density, a singularity forms. Period. The power of this theorem is that trapped surfaces do form in gravitational collapse. Penrose himself showed that a sufficiently compressed mass produces a trapped surface, and the threshold for this is related to the Schwarzschild radius. So the singularity is not an artifact of the symmetric models studied by Schwarzschild and others. It is a general consequence of the combination of a large enough concentration of mass and the requirement that energy density is non-negative. The energy condition, non-negative energy density, is where quantum mechanics enters to potentially rescue the situation. In quantum field theory, the energy density of the vacuum can be locally negative. The Casimir effect involves regions of space with energy density below the vacuum level, and the Hawking radiation calculation itself involves negative energy fluxes crossing the event horizon. Quantum fields can violate the classical energy conditions that Penrose's theorem requires. This means that the singularity theorems, which assume classical energy conditions, do not straightforwardly apply to the quantum gravitational regime inside a black hole. The singularity is predicted by classical GR under classical energy conditions. It may be avoided in the quantum gravitational regime where energy conditions can be violated. This is the precise sense in which singularity resolution is expected in quantum gravity. Not because quantum gravity is more powerful than classical gravity. In some vague sense, but because quantum fields can violate the specific energy condition on which the singularity theorems depend, and in doing so can prevent the focusing of light rays that leads inevitably to the singularity. The mechanism by which this happens, the precise quantum gravitational dynamics near the singularity, is what the various approaches to quantum gravity are trying to compute. The most interesting implication of singularity resolution in the context of the information paradox is the following. If the singularity is replaced by a finite physical region, then the interior of the black hole is not a region from which there is no exit. In the standard GR picture, information that falls past the event horizon into the interior is trapped there until it reaches the singularity, where it is destroyed. If the singularity is resolved and the interior bounces or transitions to a new region, the information might, in principle, escape, either back into our universe through some mechanism associated with the late stages of black hole evaporation, or into a new space-time region that the information effectively tunnels into through the resolved singularity. This connects to what is called the black hole to white hole transition picture. A white hole is the time reverse of a black hole, a region from which matter and light escape, but into which nothing can fall. In the Penrose diagram of the maximal Schwarzschild solution, there is a white hole region that is the time reverse of the black hole. In ordinary spacetime, white holes are unstable and are not expected to form. But if the black hole singularity is resolved by quantum gravity and the interior bounces, the geometry after the bounce resembles a white hole. Matter that entered through the event horizon during the infalling black hole phase now escapes through the event horizon during the outgoing white hole phase. The black hole in this picture does not evaporate entirely. Through Hawking radiation, it eventually transitions to a white hole and releases the information it collected. The evaporation timescale and the transition timescale may be related to the black hole's lifetime in a specific way that depends on the details of the quantum gravity model. These ideas are speculative. They are theoretical proposals, not confirmed physics. The singularity has not been observed, and the resolution of the singularity is beyond the regime of any current or planned observational program. But the theoretical necessity of singularity resolution is not in doubt. GR predicts its own breakdown at the singularity, and the singularity theorems of Penrose and Hawking prove that singularities form under general conditions. Whatever the correct theory of quantum gravity is, it must resolve the singularity. The question is how, and the answer to that question is tied to the answer to the information paradox in ways that are only beginning to be understood. Conclusion: what black holes are teaching us. Let us take stock of what we actually know and what it means. We know black holes exist. We know this from multiple independent lines of evidence. Stellar orbits around Esquire-Aik at the center of the Milky Way, tracing out paths that can only be explained by a 4 million solar mass, dark compact object. The gravitational wave signals from binary black hole mergers, matching the predictions of general relativity for colliding black holes with extraordinary precision. The direct images of M87 star and SGRA star from the Event Horizon Telescope, showing the photon ring and shadow morphology that general relativity predicts for supermassive black holes. The era of black holes as a theoretical hypothesis is over. They are observed, measured, and characterized objects. We know general relativity describes the exterior of black holes, the region outside the event horizon, with extraordinary precision. Every test we have been able to perform, from the perihelion precession of Mercury to the Hulse-Taylor binary, pulsar, to the gravitational wave signals from LIGO, has confirmed general relativity's predictions. The theory that Schwarzschild solved from the Russian front, that Einstein doubted would produce physical objects, describes the external geometry of the universe's most extreme objects to a precision that remains unmatched by any competitor. We know that black holes have thermodynamic properties, temperature, entropy, and a complete set of thermodynamic laws that demand a microscopic quantum gravitational description of their internal degrees of freedom. The Bekenstein-Hawking entropy is a real number with a real physical meaning. It counts something about the black hole. We do not have a complete microscopic theory that tells us what it counts for realistic black holes, though string theory has provided partial answers for idealized cases, and loop quantum gravity has provided others. We know that the evaporation of black holes, if Hawking radiation is correct, creates a profound tension with the unitarity of quantum mechanics. We now have strong theoretical evidence, from the island formula and replica wormhole calculations, that this tension is resolved in favor of unitarity, and that the entropy of the Hawking radiation follows the Page curve rather than rising indefinitely. But we do not have a complete, microscopic description of how information escapes from a black hole. And the firewall paradox remains a sharp challenge to the self-consistency of the most natural assumptions about the black hole interior. And we know that the singularity, the point at which general relativity predicts its own breakdown, is not a physical phenomenon, but a signal that general relativity is incomplete in the extreme conditions at the black hole interior. Whatever theory of quantum gravity resolves, the singularity will determine the ultimate fate of information that falls into a black hole. The deepest lesson of black holes is not about gravity. It is about the relationship between gravity and quantum mechanics. The two theories that each describe their domains with unsurpassed precision, and that, in the regime of extreme gravity, speak to each other in a language that neither was designed for. The information paradox is a symptom of this incompatibility. The island formula, the holographic principle, the ADS/CFT correspondence, the ER equals EPR conjecture. All of these are partial translations between the two languages, attempts to find the vocabulary in which the full sentence can finally be spoken. That sentence, the complete quantum theory of gravity, has not yet been written. It is the greatest open problem in theoretical physics. But black holes have given us more precise constraints on its form than any other physical system. They have told us that space-time must be emergent, that information must be preserved, that the interior of a black hole must be encoded in the exterior, and that the geometry of space and the entanglement structure of quantum information are, at some deep level, the same thing. There is something profound about this. For most of human history, the sky was a surface, a dome above, painted with stars, the limit of the observable world. With the development of astronomy, That dome dissolved and the sky became an infinite volume, full of stars and galaxies extending in all directions. With general relativity, the volume of space itself became dynamic, curved and warping, expanding and contracting, with a history and a future. And now, with black holes, we have discovered that the volume of space is not even primary, that the three-dimensional interior of space-time is encoded in a lower dimensional boundary, that the geometry of the world is a kind of shadow of a deeper quantum information structure that we are only beginning to understand. The photograph released in April 2019, that orange ring around a dark center, is not just an image of a black hole. It is an image of the limit of the observable universe, the boundary between what we can know and what we cannot. And the shadow in the center, the absence, the hole in the light, is not an absence of information. It is information, encoded in a form we are still learning to read. The strange mystery of black holes is that they are not, in the end, primarily about darkness. They are about what darkness reveals, the structure of space and time and quantum information at the deepest level we have yet reached. And the revelation is that the deepest level we have yet reached is still not the bottom. We are still learning what black holes are, and what they are is stranger and more illuminating than anything that has fallen in.